Good afternoon. So quiz 3 was set last night, so I can tell you what's kind of on it. So I assume people are interested in that? Yes, okay. So it will be like a scheduling multiple choice, which will be fairly quick and simple. So that will be a multiple choice on scheduling. Then there's going to be like 10 multiple choice virtual memory-ish related ones. Then a kind of short written answer about scheduling. So here's a scenario, probably like what's the benefit, what's the drawback. And then there'll be a page replacement question, where you should probably know optimal, least recently used, or FIFO, depending on your luck. And then there is my fun paging question, which shouldn't be a surprise given last lecture and the one before that. So you can expect multi-level page tables. You can expect that I was somewhat nice, that I was nice to you and didn't make you have to write in binary. So as long as you somewhat know hex, you should be good. Yeah.
So the first two written one, you don't really have to do any like calculation or anything. You just kind of talk about like what's good and what's bad.
Yeah, well, the first scheduling one will be multiple choice, and then the other one, yeah, the other scheduling one, like what's good, what's bad. And then page replacement, you need to do the full-blown thing.
Right. Kind of like the example we did.
Yeah, so how many page faults, you know, here's what's in memory at what given time, what gets replaced. Yeah.
For these like quizzes, would you ever accept like us just like doing like rough work on like another piece of paper and just like maybe like provide a way for us to submit that as well to show our work?
Can you do that on Quarkus? The question is if I can like write a PDF and.
I think another group, another classroom like in first year or something, like they did like a separate like assignment thing so that after the quiz you can submit your rough work. But has to match your final answers and stuff, so like, can't do stuff like that.
You can email Ashvin. I haven't heard of that. Yeah. Do you have a question?
I was going to say the same thing.
So, like, you just submit a random PDF at the end and it's supposed to match?
Like after the quiz, you got like 10 minutes to submit your rough work, and then they can look at it to give you 5 marks.
Maybe like for like example, like short answers, sometimes like showing your work process and stuff, but like actually drawing out like all the page replacement, like things like specifically at this point, what's the table look like? So like our rough work and process and stuff, I guess.
You can email Ashvin because he'd have to set it, I assume, and I have to commute, so my internet will not be good probably until you start. Yeah.
For the clock algorithm.
Don't worry about it. Huh?
I just have a question about like they mentioned like a dirty bit because I understand like the reference bit, but what exactly is the dirty bit doing? Because it says like if that's set, we have to schedule page rate. I don't know what that means.
Who said that?
Like I don't know. One of the lectures I was going through again.
Oh, so when you get into the implementation of it, sometimes the pages in memory or data on disk will be inconsistent. Dirty just means that there's a modification. It means you need to write it back out.
Okay.
So like, say you have the page already, like it's been on disk and you swap it back into memory. One thing you can do is just keep it around in disk. And when you bring it into memory, if you only read from it and you never write to it, well, you don't have to write back out to disk because it's already there and it's not modified at all.
Okay.
So you could just not bother. But we didn't go into that much detail. And yeah, for the quiz, if a clock would take longer than all the other ones, probably combined. So you can assume if you get randomly assigned one, having clock would kind of suck if you were the unlucky soul that got that one.
Which we might get assigned clock.
No, you wouldn't, because it would be super unfair to whoever got assigned clock and has to spend like, 30 minutes of their life doing that.
So when we do least recently used, we do like the theoretical best, like not the approximation of least recently used.
Yeah, you just do straight up least recently used. Even if it would be super expensive to implement, well, you can do it on paper because it's like 4 pages or something like that. All right, any other quick quiz questions? and it's 40 points instead of 30, so it's not like quiz 1, but so it's somewhere in between. Yeah.
So for something like a scheduling problem, for instance, like it just goes in like 1, 2, and then at time 2, let's say another process comes in. Do we do the comparison between this process and currently running stuff, or is it like this thing doesn't actually get compared until after this?
For what algorithm?
Just in general, like, do we like consider like newly inserted stuff at the time they're inserted or after that time?
So so the question's about the scheduling, and if a new process comes in, do you need to consider it?
Like, let's say at time equals 0, we have a process running process, and at time equals 1, another process enters, right? And at that time, if it's like something like preemptive, where we have to compare like their priorities and stuff, if the first one has less priority, would it just immediately be preempted too?
So like at time 0, process A is running and then B comes in?
Yeah, and then would we be like B is coming in, but like A already got scheduled in, or is it like B comes in before A, before we decide what to run?
Well, it depends what algorithm it is. If it's like that dynamic example I went through, well, A would be scheduled first because there's no choice, but then now when B arrives, if B is an absolute higher priority, it's going to get scheduled in that time slice. If it's like that dynamic feedback one, if B had a higher priority, it would get scheduled, right, until it goes to sleep. If it was round robin, oh, that doesn't line up anymore, whatever. If it was round robin, B would just be added to the back of the queue. And it would depend on however long your quantum length is as to when A gets added back to it. So if the quantum length is 3, it's going to go like A, and then this is our queue. It's just B, and then at time 3, A would get re-added to the back, and then it would be like B, and wouldn't execute immediately because it still has time on its length if it's round robin. Yeah, it'd be in round robin. It'd be added to the queue immediately. Yeah.
So if it was added right at the quantum length end, it comes in, or
Like,
it's added to the queue before A is re-added. Right?
yeah. So if there's a tie here and B or A gets requeued while B arrives, you always put the new process first because you may as well. It's not going to really affect the waiting time of A, so you may as well get good response time for B and put it in first. Yeah.
So like, let's say B arrives in between the two times, right?
What, like here?
No, like while A is still running. Like let's say like between 1 and 2.
Well, like here in the middle, doesn't matter.
Yeah, like.
Or sorry, B.
We assume like the scheduler is running asynchronously, and then like it just gets added immediately, or does it get added at that time slice?
The net effect is the same. If you assume it just gets added at 2, it would get added before A gets requeued anyways. So it's the same effect. It doesn't matter.
So like my question really is like if multiple processes arrive between a time frame, like it somehow keeps track of the order.
Yeah, they'd have some arrival order. So that'd be told to you, or like just assume they're arrive in this order. Yeah.
So what's exactly the difference between average wait time and average response time?
So response time is the amount of time it takes in order for you to start executing at all. And wait time is the total amount of time you're waiting before you're done.
And that doesn't include like the actual time you spent executing?
Yeah, it's excluding it. So
it's like if we have like A and then BB and then A, BB, but we include the first two BB?
so if you say you arrived at time 1, your process B, and then something else is scheduled here, something else is scheduled here, and then you do B, and then something else, B, and then say B's done here. At this point, this is when B arrives, so it would have 2 for its response. So it just takes 2 time units till it starts executing, and then its wait time is just between it starts and it finishes, how much time is it not executing for? So in this case, it would be 4.
All the time when actually executing.
Yeah, so it excludes it. So the wait would be 4 in this case.
Oh.
So easy way to do it if you don't want to count all of them. It's just like how long it took from start to finish minus how long it actually took to run, and that's how much time it is waiting for. Yeah.
On a single core machine, while like a specific process is running, how are the other processes that like either need to get like put onto the end of a queue for round robin? How is the OS dealing with that if they're not, if the OS itself isn't running because it's a single core? So it's just that one process is running, but it also needs to deal with other processes being ready to run next. Like how do they queue them in?
That's kind of what you did in your lab, right? You had to pick which thread to run in lab 3.
Right. So like,
So whenever the timer interrupt happened, you got control back, and then you can fiddle around with it and do whatever you want.
okay.
And then you pick.
Oh, so the OS can gain control while one thread is running.
Yeah,
Okay, right.
yeah, it'd do the same thing. So it would have a timer interrupt every like quantum length or whatever.
Right.
Or that process, if it calls exit and you're the kernel, you get control back because you get any system call, you execute code. So it's going to block. You could make it so like every system call you call or they call, you just like terminate it and let it do something else.
Response time is 2 in this case.
Yep, response time's 2 in this case.
Like it just doesn't care if they execute something. It's just first instinct.
Yep. Yeah, arrival till first execution. Okay, so let's, I guess, quickly go over that, and then we kind of bleed into office hours. So this is a bit of a weird one. We'll talk about hard disk drives. Does anyone even use hard disk drives anymore? Any data hoarders in the house? No? Okay, so this should probably be cut from future offerings because no one knows what the hell these are. But anyways, it looks kind of like this. So this is like old school storage where it's not actually flash RAM or anything like that. It's like actual mechanical spinning pieces of metal. So in a hard disk drive or an HDD, like the big chunky things, the inside of them will look like this. All the data is stored on metal disks, and they're called platters. And then within, if you took apart the hard drives, there's going to be multiple disks or platters in it. And then there's going to be like this giant ARM assembly that has a magnetic head on it that can move back and forth. And it can read, the magical magnetic bits that are set on that disk. So there's going to be multiple platters, multiple read and write heads that can read the magnetic information off it. And then if you want to actually address things, so hard drives kind of work like pages, so they have like a smallest unit, and it's typically called a sector, and they'll have a set size. So a sector is something on a track, and a track you can think of as just everything on the same radius. So you have the same radius, that's everything on the same track, and then that track will be made up of different sectors, which is essentially like the degree into that track. And then how it works is the read-write heads there, they don't move back and forth, they just move up and down, so they can select what track they're reading. And to select a sector, the whole platter has to rotate, so there's a big motor in it that actually physically rotates the disk. So if you want to read some information, you adjust the head to the right track, and then you have to rotate the disk around until that sector comes under the head, and then you can actually read the data or write the data.
Will this be stationary when reading?
Sorry?
Will it be just like spin this, it spins to it, and it will just stay stationary while reading it? Or?
No, typically the disk will just keep on spinning. They might slow down a little bit, but if it completely stopped, then it would be like start, stop, and it would like need brakes or something. It'd be kind of weird. Yeah.
Wouldn't the inner sectors be faster, like the inner tracks, when you access it?
Yeah, so there could be more sectors the closer you get to the inner size, or they could be just wider too, to fit as much the same amount of information.
But then you'll be able to read and write faster as you go inwards.
Yeah, that gets, yeah, because it's closer to the center, so it'd probably be less sectors in the middle and probably faster to spin. So yeah.
So do you put like critical stuff in there?
So it depends how tricky you get. So there's some optimizations you can do. We're not even going to do them, but yeah, that's things you could do if you're the kernel and you have absolute control over it. Maybe you want to put things you care about more closer to the center because that might be faster. Or if there's more sectors on the outside edge, since it's rotating anyways, that will actually go faster, or no, that'll go slower. Yeah, so put on the inner. So you could do that. That's just kind of what a hard drive looks like. So that's kind of this good point. The access speed depends on locality and like where it's actually located on the disk. So sectors, that are located together in the same track can be read continuously because the read-write head doesn't have to move. And as it's rotating, it's just rotating, so it can just completely just read everything, read or write everything as it's just spinning, and it can do that continuously. But it will be really, really slow if you deviate from that. So if you need to switch tracks, that head has to move back and forth, which will take some time because it's a mechanical thing. And then it also needs to rotate. So if you wanted to optimize things the old style way, which is like really, really old now, to address these things is you essentially get 3 coordinates. So you get cylinder head sector. So when you are accessing the disk, you specify each of those coordinates. So you tell the disk which platter you want, which is like what cylinder, so which revolving platter, then which track, so which lane there, which is basically just picking the radius, and then what sector you want, which is the degree again. So historically, that will only let you address things up to an 8 gigabyte limit because it assumes that there's like up to 512 bytes in a sector, 63 sectors on a track, 255 heads. So that's how many like tracks per cylinder you have, and then up to 1,024 cylinders. And then with that, they're like, wow, that's too complicated. Let's simplify that. So then something came along called logical block addressing, and that just uses a simple index number to address a sector, and then you can just address as many as you want, but you don't know actually where it's physically located now. You're hoping the vendor actually did something sensible. So along with something sensible, so if you are a data hoarder, one of the technologies for these spinning disks is called Shingled magnetic recording. So the read-write head's kind of only right in the center of the track and has some unused padding. So most hard drives look like this, where it writes little strips, and the gray is the actual data, and the white is just some padding. So because it's essentially magnets, you might interfere with your neighboring track. So there's some padding between them so that you don't overlap, and while you're writing information to one track, you don't disturb another one. So that's typically what you have, but with this shingled magnetic recording, it allows you to kind of write over the padding if you do things in order. So if you do it sequentially. So on the right there, that shingled part, it might only interfere at the bottom. So if you write these kind of like shingles, so you write the first track and then the track below that and then the track below that, you won't disturb what's above you, but you would disturb what's below you. So if you write them in the right order, you can fit them closer together and get more density, but it's also going to be slower depending on how you use it, because say you shingled those 3 things, you have to write the top one, then the middle one, then the bottom one. And if you wanted to change data just in the top one, well, if you just change data in the top one on this one, you would disturb the track below you. So you have to, if you want to modify it, you have to write the one at the top and then rewrite the one in the middle and then rewrite the one at the bottom. So it's really, really slow, but you can pack information closer together. And funny story, because this is much, much slower and annoying, the first time a company used it, they didn't tell customers that they used it, and they bought it and the performance was awful because the kernel didn't know about it either, and they sued them because the performance was so terrible. So, fun story. But for most conventional hard drives, all their latencies are going to actually depend on the distance traveled because the thing's spinning and you have to move ahead, back and forth. So typically, it's going to have two types of delays. There's rotational delay, so to physically rotate that disk to get to the correct sector. And this is where we actually know the numbers for milliseconds. So this makes sense why it's so slow, because it actually has to spin. So typically it'll be like 4 to 8 milliseconds to actually rotate the disk once around. And the average delay is going to be like half of a rotation if you're assuming, it's random and fairly uniform. Then the seek time is moving the disk arm to get to the track, which is faster than spinning the whole platter, but still kind of slow, where it's like half a millisecond to 2 milliseconds. And then the transfer time is how long it takes to read bytes from the disk, assuming everything is sequential and it's as fast as possible. And for these drives, your maximum transfer speed probably going to be around like 125 megabytes a second, while your NVMe drives are probably pushing, if you have a new one, like 7,000 megabytes a second. So comparatively, much, much slower, but hey, it's much cheaper too. So if you were to calculate the transfer rate, they're fairly self-explanatory formulas. So you take the total time, and the total time is going to be equal to all the moving parts. So you have to include the rotational delay, the seek time to move the head back and forth, and also the transfer time that it takes to actually transfer that data. And then once you have that, your transfer rate is just equal to the size of the transfer, however much data you transferred, divided by how much time it took. And then we can answer questions, well, what's the transfer rate of large sequential accesses and then small random accesses? And then we'll see why these things are actually decent for hoarding videos and terrible for putting your kernel on it. Yeah.
When you say like memory lives like sequentially, do you mean like they live on the same track, or do they live like vertically at the same?
Yeah, sorry, by sequentially I mean on the same track. So while it's spinning, the head doesn't have to move and the disk is already spinning.
Right.
Yeah.
But is there something that is stored like horizontally maybe on the same sector? Like they align it?
Yeah, so all the heads are aligned. So there'd be one head per platter.
So like when you have like an array, right? Like say they're stored sequentially disk on disk. Like do you do it by track, or do you do it by like?
So you do it by, you access information by sector. So if you had an array, it would probably all be on one sector because they're like, each sector is 512 bytes. So it deals in sectors and blocks and things like that are going to be bigger units.
Right, and then when like you say it's consecutive, you mean like they're on the same track?
Yeah, on the same track. Yeah, so this is to illustrate to use hard drives sequentially whenever possible. So here's two versions of disks. So the rotational speed on consumer devices, you'll hit like 7,200 RPM, which is 7,200 rotations per minute of that spinning thing. And then that will translate to a rotational latency of like on average 4.2 milliseconds. Average seek time would be like 9. Max transfer would be 105 megabytes a second. Then have 4 platters and you don't have to worry about the interface. And then like hard drive 2 would be a more enterprisey one that goes at 1,500 rotations per minute, so almost twice as, or more than twice as fast, which would mean its rotational latency is only 2 milliseconds. Its average seek time would probably be more than twice as fast too, although they might not be related, so it'd be like 4 milliseconds, which a max transfer speed, that's not that much different, like only 125 megabytes a second. Then if you actually compute these things, well, For sequential accesses, you can assume that the rotational time and the seek time are 0. So in this scenario, you're essentially given the transfer rate and then given how much data that's transferred. So you just have to calculate t. So you just take the data, divide it by the transfer rate, and then that's how much time it takes. So for hard drive 1, that 100 megabyte transfer would take like 950 milliseconds. And for hard drive 2, 800 milliseconds, which is a bit faster, but not that much. Then the case where you would want the enterprise drive is because it's way better for random accesses, although both of them kind of suck. So if you're just to read a random 4 kilobyte page, so say that was you swapping something to disk, well, if you're just accessing a random 4 kilobyte page, well, even if we assume the transfer time is instant, just to make our lives easier, that it's 0, so the total time, just assuming a random access, would have to be the rotational time for hard drive 1, which is 4.2, plus the seek time, which is 9. So 9 plus 4.2 is 13.2, so that would be our time. And then we would be transferring 4 kilobytes. And then if we figured out the rate based off those two numbers, we would get 0.3 megabytes a second, which is horribly slow, which is also why you don't really want paging. Well, you don't want to swap to disk, especially back in the day. So this would be better now that you have SSDs. That will touch on next lecture because SSDs are a bit weird. But this shows kind of the big difference between them. Yeah.
But like for the sequential access, if you kind of store your data like horizontally, like and utilize all 4 platters, like wouldn't that like quadruple your speed if you can like use all 4 heads to do the same?
Yeah, but you'd also have to know the layout of the disk and kind of optimize it. If you use like the just index to, you just get a random sector based off the device, you won't know.
So like the newer way, by just having like index, like you can.
Yeah.
The OS can optimize everything.
Yeah, the newer way by just having an index, you have no idea. And also, hard drives historically fail. So sectors go bad all the time, even without telling you, and you can still use the device. So even if they lined up before, they might not line up anymore because hard drives will take a bad sector and just remap it somewhere else without telling you about it.
So you can't rely on ordering.
Yeah, you can't rely on ordering.
And then the same thing can be said about having sequential data, because they might be sequential at one point, but then at a later point they might not be.
Yeah, but typically if they're sequential, try and keep it sequential-ish.
So what
Yeah.
exactly do you mean by they go bad? Like the strips just stop working, or?
Yeah, by bad, so I haven't taken electromagnetics in a long time, so I don't know the mechanics of it, but essentially the magnets fail. I don't know.
And then also it's like a lot of like the old like quote-unquote antivirus software and stuff are like saying, oh yeah, it will help defragment your hard drive. Like what does the fragmentation of hard drive exactly mean?
So defragmentation hard drive, we'll see more when we get to file systems, but not much. But we know what the word fragmentation means now, right?
Well, no.
No, we know what's fragmentation mean? There's like some gaps in between, right? So if we have a spinning hard drive and we want everything all together in a single row, well, when we're accessing files, it just essentially deals with big like sectors, which you can think of as just blocks. So as you're using it, you might create little holes here and there where your file gets chopped up and it's stored on different blocks and it's not actually all sequential. So if you defrag your hard drive, it will try and make sure that all the blocks that represent your file are actually sequential. Yeah.
So in general for HDD, you're gonna have sequential. Sequential is like okay access time, and
It's,
random is really bad.
Yeah, random is horrible. So if you use these devices as sequential, they're not too bad. But they're still not as fast as SSDs, but they're still way cheaper.
Okay.
Yeah.
Like, since you're using magnets, I don't understand like how that you just take a magnet and move it around the computer. Is that like a good idea?
Yeah.
Okay, let's show it.
Yeah. Anyone watch Breaking Bad when they went and, oh wait, I won't spoil anything. But anyways, like back in the day, you can destroy computers by just bringing a magnet close to them.
You can't do that anymore?
We don't have magnetic drives.
So that was only because of the hard drive that you were messing up stuff.
Yeah.
So you would lose data when you just.
Yeah, so if someone takes a high-powered magnet and sticks it on your hard drive, well, because it's storing it magnetically, it would screw it up, so your data just gets random stuff, and then you don't have data anymore. So like your iPads or whatever, I mean, if you take a magnet to that, it's fine. Even the accessories are magnetic. So back in the day, we weren't allowed to have magnetic accessories because we'd blow up our devices. So if you have an old iPod or whatever, the original iPods had a spinning disc in them. So if you brought it too close to a magnet, there go all your songs. Yeah. Damn, I feel old now.
I just thought that was still a thing. Because my mom always got mad whenever I brought magnets around things.
All right, someone was just walking around in their home with magnets.
Do not. Magnets are fun.
No. Okay, people like playing with magnets. All right, learning something new every day. Okay, so with the logical mapping, so when everything is just numbers, what you would hope to do is place all the numbers so that they're actually sequential. So if you access everything, sequentially in terms of the numbers, they're laid out sequentially in terms of the disk. So if the disk spun, in this way, counterclockwise? Yeah. So you would expect, clockwise. If the head's there, you would expect, if you're reading 0, then 1's next, 2, 3, 4, 5, 6, 7, all the way to 11. So you could read that sequentially, get your max access speed. And then you would want it such that when you switch from 11 to 12, that's that's as fast as possible. So if you're designing the hard drive, you probably want to take into account the time it takes to move the head one track forward while it's rotating, so everything lines up, so you at least get an access as quick as possible. So you line up 12 so that it's kind of in line with when the head settles down, and then so you can access 11 to 12 as quick as possible, and then 13, 14, all the way to 19 would be all in a row, and then same thing with 20. So you want to lay it out so that it's the most efficient, where you kind of minimize the amount of time that head's moving. So the pros of that is it's really simple to program. You just access things sequentially in terms of indexes as much as you can. The default mapping aims to reduce seek time for sequential accesses, but the cons are kind of like what you said. The file system can't inspect to try and optimize anything and like really truly try and lay it out, or try and have data under the same data that's accessed together under multiple heads at the same time. It's never going to be able to figure out that. And if you try to reverse it, it's also going to be a pain. So maybe you can keep track of, the time between two sectors is longer than the time between most of the other sectors. So it's probably changing tracks there. So maybe I can figure that out. But like I said before, sectors go bad all the time and the disk can just silently remap them. So just because you figured out maybe where the track changes, that might not always be the case.
So if it silently changes, don't we just lose access to where the thing is, or does like the OS know about it still?
The OS wouldn't know about. Typically, it was able to. It kind of detected it was going bad, like it was getting weaker, so it would have just copied the data to a new sector and then just remapped it, and then it stops. Yeah, it would do it. So if it failed at doing it, it would tell you and then report to the operating system, oh crap, you've lost data. But if it silently remapped it, it'd be like, yeah, no, it's fine, don't worry about it.
So essentially, if you try to do the old address, it'll just get sent to this one instead.
Yeah, and then it would never use the bad sector again. Yeah.
What does like reverse mapping mean? Does that mean like if you have it getting back where your data is supposed to be, or?
No, reverse the mapping means you try and figure out where things are located just based off kind of the index numbers.
Oh.
Like you're trying to reverse engineer whatever mapping they used. So what we could do is, like we always do, just throw a cache onto it. So this is another cache we can talk about. So disks will have some internal memory on them that would be like a flash. So for like Western Digital Red ones, they have like 40 or 64 megabytes of cache. And basically what they do is, since the data is under the head anyways, it would just keep on reading it and filling up that cache. And if the kernel decides it wants to access one of those pages, well, it would have already been in a buffer and already read. So it could just send that straight to the kernel from the memory without having to read it again, since it's essentially just reading it for free. So you can do that, and that will kind of minimize, kind of hide that, and you get some nice speedups for free. You could also do some write caching with volatile memory, like going to disk. So you could just say you have a page on disk that's supposed to map to a sector on the hard drive that might represent a file or something like that. Well, if you modify that file, it can just, instead the kernel can just, modify that page on disk, and then the idea would be that it only writes it back to disk whenever it pages that out, or whenever that file, you close that program and that memory gets deallocated or something. So that would be called a write back. So whenever you modify a file, it doesn't actually physically write to disk. It just stays in memory until you either close that file or it gets remapped or something else happens to it. But if you do that, it's going to look fast because all your writes are going to actually be to memory instead of disk. So that's going to look really fast. But because RAM is volatile, if you have a power failure and you modified a file and you just modified it in memory and didn't actually physically write it to disk, if your power goes out, all your changes are now gone. So for normal caches, that's all volatile anyway, so if the power goes out, it doesn't matter. Right, your CPU volatile, RAM's volatile, Yeah, so this would be, hey, I modified a file, it didn't actually get modified on disk. It's just waiting to write it out because writing's slow. You want to like accumulate all the changes or just do it all in one big go at the end. So write back, if your power goes out before you actually write it to disk, then you actually lose data. So if you're designing a file system or something like that, you would want to know if you have write back or not, or if you have a database, a program representing a database, you might really care about the data and you might want to make sure it's actually written to disk. So that's something called write through, where you tell the kernel, hey, I mean it, write this to disk right now and let me know about it. So then if there's a power failure, you're not completely screwed because you know it's actually physically written to disk.
So write through is it's an indicator that it should be written immediately?
Yeah, write through means skip the cache, write directly to the disk. Because I actually care about this data. If the power goes out now, I don't want to lose things. Yeah, so like processes, there's going to be requests for sectors, and if you're the kernel, you get to schedule them. Because you're you issue commands to the disk and say what sectors you want to write, so we don't escape scheduling. So if you just have a list of sectors you need to access, well, there's different ways to schedule that. You can do first come, first serve. That's always an option. So that's going to be fair, but it's essentially going to be fairly random, especially if you have a multiprocessor machine, that every program is using different sectors. So you're going to spend a lot of time waiting for the disk to rotate and waiting for it to seek because all the sectors are going to be located in different spots. So if you were a bit more clever, you could do something like shortest seek time first, which is just to handle the nearest cylinder or sector next to try and reduce the amount of arm movement, but that can be unfair and you starve some requests. So the idea behind that is, you'd only access the next, if you're reading a sector, the sector you would access next would be the one that you can make it to in the fastest time. So if there's just a cluster, say, on the inside of your disk and there's one sector on the outside, well, if you had a bunch of accesses that were just to the inside, it would prioritize those and only stay reading sectors on the inside and keep the head down by the bottom and never read the thing that is far away, which would be another case of starvation. And starvation is an issue for any scheduler, especially the ones we already saw before. So what you can do for a different scheduling algorithm is something called an elevator, or aka a scan. And all it does is basically sweep across the disk and keeps the seek head moving in the same direction. So like an elevator, if it's going up, it's only going up. It doesn't go back down until it's done everything. So in this case, if we have requests for sectors 0, 12, and 20, it would even, no matter what order those requests came in, we would start our elevator at the bottom. So start at the outer track. We would read sector 0, then move it up one track, then read sector 12, then move it up one track, and then read sector 20. And then with this too, so say we also had a request for sector 6 as well. Well, with this algorithm, it wouldn't be terribly smart because it would read sector 0, then wait for the disk to spin halfway around, then it would read 6, and then it would reposition the head to the inner track, or to one track in, and then wait for the disk to spin back halfway around to make it to 12 again, and then it would read 20. Yeah.
So what if it's like 0 and then we have the 6, but then like we move to 12, but later on like a 7 gets put in, like we can't move back. Yeah, so we have to wait until we finish the 20 before we move back to the 10 again?
Yeah, so the way the elevator works, so even if I read 0 and then I went to 12, if I moved the head to the 12 track and a request came in for like 1, 2, and 3, I wouldn't move back down until I've made it to the top of the elevator and then it comes back down. So that's just a way to make it fair. Otherwise, you would have that starvation if you just kept it on the same track or went back down. So that's one of the things this tries to avoid. So the elevator, sometimes it's called shortest seek time first because it's trying to minimize the head actually moving back and forth. So the optimal thing to do that has that starvation issue, so it's kind of like doing shortest remaining time first when we're talking about processes. So shortest positioning time first would be the best strategy, which would take into account both rotational and seek time and try and minimize that to actually go to the next sector that is the absolute closest. But in that case, the kernel and the disk would need to work together to implement it, which if you don't know what the mapping is, that's going to be impossible to implement anyways. Yeah.
So for the elevator,
Mm-hmm.
start at 0, we go to 6, and then we go to the next one. Don't we have to go all the way back and go to the next one?
Yeah.
Oh, okay. So like when you said it goes to 6 and it goes to the next one, just like an example.
Yeah. Yeah. So in this case, if we had all these accesses plus 6, if we wanted to be super fast, the quickest thing to do would probably be read 0, 12, 20, and then move the head back to the outer track and let it rotate just half a rotation, and then read the 6. But elevator is going to wait, it's going to read the 0, then rotate halfway, read the 6, wait for another half rotation to read the 12 and then the 20.
Why can't we just have a head at every sector?
So the question is, why can't we just have a head at every sector? Because a track at it.
Every track, just have a head.
then you wouldn't need to spin.
No, you still need to put it on the track.
It would just be like
But if you have one at every sector, you
one
can
at-
just
no,
read the
no,
sec.
one at every track.
One at every track.
And have like everything rotating.
So,
Just have like,
They're just for reading from
this.
yeah, so question is, why don't we just have a head at every track?
yeah.
I believe the heads are way bigger than the track and are actually fairly complicated and expensive. Yeah, although I personally haven't made any hard drives myself. But I imagine that's probably why.
But they don't even have to be like on the same, like, they can just be like stay there.
Yeah, so you optimizing, you might be able to optimize a hard drive, but it's going to be like ridiculously expensive probably, and still lose to an SSD now. That we'll talk about SSDs next class, because apparently we run around with magnets. What?
So are hard drives still like the cheapest for the largest storage currently?
No, tape drives are.
Okay,
Yeah, but so no, it's like a big cassette.
oh, really?
Yeah.
And you can just like read from it just by like unwinding it and rewinding it.
Yeah.
And that's why it's slow. But it's like
Yeah, but they can hold like terabytes. Like, so Google's archives use big cassette magnetic tapes, and each tape is like really cheap and holds like terabytes. But you actually have to like, if you want to get data, you should actually, you can probably find this on YouTube where like you see it just is a wall of tapes, and to read a tape, it has to go get the tape, pull the tape out, put it in the tape reader, and do all that crap. And
Wait, so does any Google search cause that to happen? Like if I Google search something really obscure, will Google do that for me to get more data or no? Like why does it have that if you like?
so it's mostly for archival stuff. So if you detected something that's like in their archive, well, it'd probably give you a response that's like, no, I don't have that. And then in the background, it could go grab the tape and then, read it and then make it all live again and do whatever. So the next time you do that the next day, it works.
That's cool.
But it's like for stuff they want to keep around. Yeah.
the elevator is also the shortest positioning time first.
Shortest seek time first. So just the head. It doesn't care about rotation. Yeah.
I was gonna ask like, how would they even know which tape?
I do not operate at that scale. So when you get an internship at Google and you can like somehow get into the data center, which they probably don't let interns do that, then you could probably see these things.
Walk around with magnets.
Yeah. You think Google's going to let you have a magnet in their data center? Yeah, you think your mom yelled at you. Just wait till your mom gets armed. All right, so that wraps up. So disks are things that enable persistence, and that's one of the like 3 major topics of operating systems. So we saw the spinning disks today, like basically 2 of them, like the enterprise, there's like enterprise versions of things, there's the shingled magnetic recording versions of things. But basically they all have really poor random access time. They need some scheduling because you'll be accessing sectors. And the best scheduling would be to do something like shortest positioning time first, but that's going to have starvation issues and not really be too feasible. So just remember, I'm pulling for you, we're all in this together.